Hey AP, this video is on intermolecular forces. So in the last unit, we talked about intramolecular forces, which was our left side here of our types of bonding flowchart. We talked about ionic intramolecular forces, covalent ones, and dative or coordinate intramolecular forces. So this is what we've talked about so far. Remember, intra was within or inside of our compounds. In this unit, we're going to talk about intermolecular forces, and this is interactions between two different molecules. So we can have three different types: hydrogen bonding, dipole-dipole, or London dispersion. Hydrogen bonding is the strongest, and London dispersion forces is the weakest. And we can see that up here, from strongest to weakest. That's going to impact things like melting point, boiling point, viscosity, vapor pressure, right? Things that are held together stronger are going to require more energy to separate. And we are breaking interactions, right? These are interactions between molecules, whereas before these were bonds. Okay, so we're not breaking bonds or looking at bonds. We're looking at interactions from one molecule to another molecule and how they interact together. So starting with the basics, we have types of molecules can be in three different states of matter. We can have solids, liquids, or gases. Solids can either be crystalline or amorphous, and we'll talk about those below. But most importantly, solids have a definite shape and volume. So I can see this here. My solid is in some sort of lattice form, is in a definite shape. It stays here. My particles vibrate in place a little bit, but they stay in their same shape. They have a distinct volume. Liquids, however, they have one volume, right? Definite volume. These fill my container, okay? Or maybe they only fill half the container, but they have some sort of volume. But they have an indefinite shape in that they take the shape of their container. Gases are special in that they don't have a specific shape. They take the shape of their container. And also, if you put these 5 gas molecules in the classroom, they would fill the classroom. They'd spread out until each of them were spread out among the classroom. Or if you put them in a tiny little jar, they would spread out as they would inside the jar. So we say it's an indefinite shape and volume. So getting back to solids, solids can have a crystalline shape, which is where there's regular ordered, repeatable 3D structure of particles. So like ionic compounds, when they make a solid, they make a crystalline shape, which we've talked about. Or amorphous types of solids, those are particles not regularly ordered. So thinking of things like sandstone or mud when it solidifies, right? It's just got a hodgepodge of molecules put together. They're not ordered in some sort of specific fashion. Liquids, we say those particles are in an intermediate state. Just to come down a little bit more. Okay, an intermediate state. And that means that they're not stuck in one place. They're not zooming around. They kind of just slip and slide past each other. Some properties of solids and liquids, those are always going to depend on how the particles are arranged and the attraction between the particles. Stronger attraction is going to impact our solids and liquid properties. Now, gases, these particles have so much energy that they're going to overcome any sort of intermolecular forces, and they'll move around freely with significant space in between them. And that's where we get into the kinetic molecular theory, and that's when we'll talk about that along with our gas laws later on in this unit. All right, intermolecular forces. Let's start going through some different types. Well, intermolecular forces are based off of electronegativities and dipoles of my atoms within my molecule. Based on their arrangement, that can make my molecule have dipoles or not. And if it has dipoles, it's going to have different interactions with the other molecules versus if it doesn't have dipoles. So remember that electronegativity is the ability of an atom in a covalent bond to attract electrons to itself. We have polar bonds when one atom attracts more electrons to itself than the other one. If we have elements with electronegativities that are different but basically similar, so let's look at if we have carbon and hydrogen, 2.5 and 2.1, they're really pretty similar. Okay, we are going to consider that to be basically equally shared in nonpolar covalent. Okay, now we know that that is slightly different than if we have a diatomic molecule, right? That would be perfectly nonpolar, but these are more or less nonpolar because they're more than likely going to cancel out with something else. Okay. Now, if we have unequal electronegativities, then we're going to get an electron cloud distortion. Excuse me. So remember that electrons aren't just in one location. They're buzzing around our atom. Think of like that cloud of bees, right? Swarm of bees. And when I change the electronegativities and I have a really electronegative element next to one that's not very electronegative, well, my electron cloud is going to shift. Okay, and when it shifts, it's going to redistribute. So I'm going to have a redistribution of the electron cloud charge density. In other words, it's going to be denser in one area versus another. So this creates opposite charges called dipoles, which we've talked about, and makes a polar covalent bond. So if I was looking at something here, I would have, let's say we have carbon and fluorine. Well, typically, if they were equally shared between carbon and fluorine, there'd be electrons in carbon, electrons in fluorine. They would be about equal inside of my electrons, zooming around here. Okay. But we know that fluorine is super electronegative, carbon much less electronegative. On our periodic table, we can see the difference there. You could also look them up. And what would happen is less of my electrons will zoom around carbon and way more of them will hang out around fluorine. So I'd have way more electrons around fluorine and very few around carbon. So even though they're sharing and every once in a while these will come over here, for the most part, they're going to hang out around the fluorine, which makes this side partially negative and carbon partially positive. Okay, and this happens again because, well, this guy's kind of electron deficient because it's lost most of its electrons to fluorine. Even though they're sharing, it's like sharing with an older sibling. They probably took more than they were supposed to, right? Same type of thing. So depending upon how much is shared or not shared, that's going to depend, or that's going to determine what type of intermolecular forces we have. Now, in every single molecule, so between molecules, we have London dispersion forces. And these are small electrostatic forces caused by the movement of electrons within the covalent bond that otherwise have no permanent dipole, but it's just the sharing of those electrons. Again, these exist between all atoms and molecules, so everything has London dispersion forces, or LDFs. And we can have stronger LDFs when we have larger surface area because we can have more electrons there. So if we have more electrons, increased surface area, that is going to increase higher melting points and boiling points because it makes this really, really temporary, almost like a blip of a dipole. And if I have more electrons, I can have that shift happen more easily. So if I'm looking at something like helium versus xenon, well, on the periodic table, we are looking at helium, and I always seem to not have my periodic tables when we do this. Oh, please. All right, so if we're looking at xenon and helium, right? Helium up here in row 1, xenon way down here in row 1, 2, 3, 4, 5. Okay, so xenon has 5 shells of electrons. Helium has 1 with 2 electrons. So xenon way bigger, so its surface area is bigger, and it has way more electrons. Okay, therefore, xenon is going to have a much higher boiling point of negative 100 compared to helium at negative 270. And that's because it's going to take more energy to break apart my xenon atoms from one to the next, right? Because xenon's a noble gas, so it doesn't bond most things. It just hangs out. It can take more energy to separate those than it is for helium because helium has weaker London dispersion forces. Okay. Our next in strength is our dipole forces, or dip-dips. These are molecules with permanent dipoles, so they happen between polar molecules. So if I have one polar molecule here and another one here, okay, and we have these temporary dipoles that hang out, right? This one side becomes more positive, the other side more negative. Then I get this interaction, almost like a magnet, this attraction between the positive side of one and the negative side of the other. This is the dipole-dipole interaction. It's from molecule to molecule. Okay. So a polar molecule can cause a temporary shift in electrons in a nonpolar molecule. So that can happen. It doesn't happen a lot, but it can. And this is a dipole-induced dipole interaction. That makes sense, right? Didn't have a dipole, but one came along and induced a dipole in the other one. A polar molecule can also interact with an ion. That's how we have dissolving happening. And this is called an ion-induced force or an ion dipole force. And that happens because this partial negative, right, attracts to the positive side of an ionic compound because opposites attract, and then it's going to rip it apart. And we'll look more at that in a second. All of these, because they're on attractions, rely on Coulombic attractions. So again, that's still this foundational force, just like what we talked about back in Unit 1. Coulombic attractions still apply. Our strongest type of intermolecular force is hydrogen bonding, or H bonds. Now, it's a misnomer because, chemistry likes to be confusing sometimes. This is not an actual bond to hydrogen atoms, right? No bonding to hydrogen atoms is this phenomenon. However, it's an interaction of attraction due to this temporary charge because hydrogen is really not electronegative, whereas the three atoms that it likes to bond with, fluorine, oxygen, and nitrogen, are very electronegative. So it causes a really large imbalance in electronegativities. Therefore, hydrogen loses its lone electron. It's brought to the bonding side of the nucleus and towards the other guy, leaving the hydrogen side basically empty and basically a positive charge. So if I was looking at this molecule here, R just stands for rest of molecule, and I have my NHN to it. And then this is just molecule flipped around. Well, nitrogen is way more electronegative than hydrogen. So because this exists, this bond exists, there's a really large change in electronegativities. And hydrogen becomes partially positive because it loses its valence electron to nitrogen. Every once in a while it gets it, but most of the time nitrogen has it. So nitrogen becomes partially negative. Same thing here, same molecule, just flipped around. Nitrogen becomes partially negative because it holds more of the electrons. Hydrogen, partially positive. And so we have a stronger dipole action, and it's one of the strongest ones we can have. That's why it gets the special name. And it only happens with hydrogen, so that's why it's called hydrogen bonding. And we have this interaction, and you can be asked to draw the interaction, and that happens from the hydrogen of one to the nitrogen of the other because positive, negative attracts, and the same thing here. You can also see this in DNA molecules. Fun fact. So let's look a little bit more into this. Like I said, it only happens with specific atoms, and it makes the hydrogen be considered partially charged or positively charged. So it's strongest with our fun elements, FON, fluorine, oxygen, nitrogen. And that's because these have the three highest electronegativities of anybody on the periodic table. And remember that they must have direct contact with the hydrogen atom, right? So if I have something like, carbon, fluorine, hydrogen, rest of molecule, okay? Because my fluorine and hydrogen are not directly bonded to each other, no hydrogen bonding happening. Okay, it would have to be carbon, fluorine, hydrogen, and then you would have it. But this doesn't exist, so we'll just ignore that there. Okay, but it has to be directly contacted with the hydrogen. Two super important consequences from this. These molecules have really, really, really high melting point and boiling points because it takes a lot of energy to separate the molecules. And it creates more viscous substances, which also makes sense, right? They're really thick. They like to be next to each other, so they're going to stay next to each other. And that's really, really viscous, right? So like honey has a high viscosity. It moves really, really slowly. Therefore, there's probably hydrogen bonding happening between the different molecules that are in honey. Okay. So how does this then apply to dissolving? We alluded to it a little bit before with that ion dipole force. Okay. So in order for something to dissolve, we have to overcome our solute-solute and solvent-solvent attractions, right? Our solute-solute, the thing that gets dissolved, is attracted to itself. And the solvent-solvent, right, the thing that does the dissolving, is attracted to itself. So we can think of an example of a solute-solute interaction is like sodium chloride, and solvent-solvent is like water. Okay. Water molecules have hydrogen bonding. They're attracted to each other. And sodium chloride molecules, which really are ions in ionic compounds, right, make that beautiful crystalline lattice. Okay. They're all attracted to each other. So in order for water to dissolve sodium chloride, I have to make solute-solvent attractions. And this water has to be able to come in and overcome the attractions that my solute already has to each other. And this is why things that are polar can break apart polar things because they have positive and negative ends, so they can rip apart the positive and negative ends. And things that are nonpolar can also squish in between and take apart things that are nonpolar. So like dissolves like is what we remember, but it doesn't explain what happens. Okay. We can also talk about vapor pressure. Now, vapor pressure has to do with intermolecular forces. The weaker the intermolecular force, the easier for a liquid to become a gas. That makes sense. It has a really low boiling point. So if there's a really low boiling point, it takes less energy to break apart my molecules from one molecule to the next, so it's easier to evaporate. So we can think of something like gasoline. Well, gasoline must only have LDFs. Maybe it has dipoles, but probably doesn't because it evaporates so quickly. Okay. Something like ethanol also evaporates really quickly. That does have hydrogen bonding, but it has really small hydrogen bonding in terms of other things. So, something that could be asked of you. Explain the trend in boiling points of the group 15 hydrides below. And a hydride is something that ends in hydrogen. So, whenever I'm asked to explain a trend, one, we can see that, okay, pH 3 has the lowest boiling point. We can see this one's the lowest. And then of these, looks like SbH3 has the highest. And then these two are in the middle, although this one is much higher than the other. So I might say that this is higher and this one's in the middle. So I firstly take a look and say, okay, this is about what I'm dealing with. Well, I know that intermolecular forces play into properties. So looking at these, I would say, well, everybody has LDHs. Everybody has London, or LDF, sorry. LDH is your cholesterol. It has London dispersion forces. Okay. If something is polar, it's going to have dipole. So I'd have to start drawing them. pH 3 looks like this. Also looks like this. SbH3. Something we don't use very often, but yep, it's right here. Are these all in line? Look at that. They're all, oh yeah, it said group 15. Look at that. So this guy looks like this and this guy. All right. And nitrogen, NH3, looks like that. So they're all polar. So that means they all have dipole. So dips. Okay. And last thing to check, does anybody have hydrogen bonding? Well, that has to be hydrogen to a fluorine, oxygen, or nitrogen. And we see that happening here. So this guy has hydrogen bonds. But that's weird because this guy has a higher boiling point but doesn't have the highest. So then I have to think, okay, why then does this have the highest when it should be this guy? So the other thing to think about is, well, what is different about this molecule compared to this one? This one falls in the trend, right? Of these three, this one has the highest. That makes sense. But then what's the big difference between this molecule and this molecule? Well, on the periodic table, we can see that between nitrogen and antimony, Sb has 5 rings, whereas nitrogen only has 2. So this guy is really, really, really big. And that means that if this guy's really, really big, it can make stronger induced dipoles. So it can have really strong LDFs. So antimony hydride must have strong enough LDFs to make it so polar in instances where it has stronger attractions. So we would say that antimony hydride, SbH3, because of its surface area and how big it is and its number of electrons, that factor overcomes the hydrogen bonding that happens in ammonia, NH3. And that's why this must have the highest boiling point, even though we would assume that NH3 would have the highest. And AP really likes questions like that to make you think about, well, here's my trend, but actually this is slightly different. So I guess this has to be why. And I think, is that the end? Yeah, next one starts the next type. So there you go, our 3 types of intermolecular forces.